We're going to learn about the binomial distribution today. So what are the conditions for a binomial setting? And we're going to use an acronym referred to as BINS, and you will be thankful for these acronyms at the end of the year when we're preparing for the AP exam. It helps you remember all the different things you're supposed to talk about. So this is an acronym. Okay, and it is binary because you have two possible outcomes. You know, binary, the root word is bi, means two possible outcomes. And we will label them as success or failure. And I put them in quotes because success is not always a positive thing. It's just what probability you're looking for, what you're looking for regarding the outcome. So success or failure. Independent means that each trial is independent of the next. N, number, means that the number of trials are fixed. And then finally, success means it stands for each trial has the same probability for success. So overall, this is not a very hard concept at all. So I think you'll enjoy this part of the unit. So again, just to recap, we're going to use BINS, binary, two possible outcomes. All the trials are independent for I. The number of trials are fixed for N, and each trial has the same probability for success for the S. So let's kind of talk about this in terms of some examples. So what is a binomial random variable? So specifically, what's the variable? Here we're talking about the distribution. This is the variable itself. So what are the possible values of a binomial random variable? So a binomial random variable is just a discrete random variable, which you guys are familiar with at this point, that meets the requirements for a binomial setting. The count X of successes is a binomial random variable. So let me just give you an example. We will let X equal the number of heads in 10 flips of a coin. So this sounds very similar to what we did with the discrete random variable. You just did not know yet that it is actually more specifically a binomial random variable. So how would this meet our binomial setting? So first of all, it is going to be binary, because there are two outcomes. Heads, which is going to be our success, and then, of course, tails, which is going to be our failure, just for the sake of this example. And we know that independence exists here because the flipping of one coin has nothing to do with the outcome of the flipping on the next coin. And the number of trials here is fixed. The number of trials is fixed at 10. And finally, the probability for success is going to be 0.5. So P will be 0.5 for every single trial. So we met our B. We talked about our I. I didn't write anything down for that. Here is our N, and here is our S. So yes, this is a binomial random variable. Okay, so they're not that hard to identify. However, students often forget to think about these on the AP exam, so we'll work on that some too. Okay, so what are the parameters of a binomial distribution? So we need X, which represents the number of successes. Okay, and that just means if I flipped a coin 10 times and I want to know the probability that I get exactly 4 heads, I am talking about 4 being the x here. So that's all I'm saying there. N is going to be the number of trials. And S is going to be the probability for success each trial. Okay, so how do you do this in the calculator, and what must you show to get credit on the AP exam? So in the calculator, it's going to be under Binom PDF, and this will be N, comma P, comma K. That will be our parameters. I'll tell you what all that is. So N is just the number of trials. Number of trials for N. P is the probability for success. And K is really just your X value. Now the K and the X, that gets really confusing for students, and it's because the calculator shows one thing, the book shows one thing, the formula card shows one thing, so we'll work through all that. So if I were to enter this in the calculator, it would compute the probability that X equals K. So let me build upon what I just said in our other scenario. If I want to know the probability of exactly 4 heads when I flip a coin 10 times, I would basically say I have 10 trials, my probability for success is 0.5, and then I would say I'm looking for the value of X of 4. So this would compute the probability of getting exactly 4 heads when I flip a coin 10 times. So that's what we're doing here. And I'm actually going to come back to what must you show to get credit on the AP exam. I'm going to come back to that. So what is the most common mistake students make on binomial distribution questions? They don't recognize the binomial setting. So if you get stuck on a problem and you just cannot figure out how to approach it, always think about, is this a binomial distribution? Is this a binomial setting? Would bins fit? And I have actually seen this over and over. When we practice for the AP exam, students really do have a hard time recognizing this. But once you start to think about that as something you can pull out of your back pocket to try, it really does help. So we'll go over that some more. Okay, so let's do an example. So we are basically here, we're going to determine, do we have a binomial setting? Is this a random binomial variable? So we're going to roll a fair die 10 times and let X equal the number of 6s. So in this case, let's kind of go through, is this binary? And it would be yes, because either you get a 6 or not. So I realize you have 6 different outcomes on the fair dice, and it doesn't have to be where you use all 6 of those for your outcomes. Here we're saying a 6 or not, where 6 is the success outcome. Okay, so I is independence, and yes, that condition is met. That's kind of hard to say how you're meeting that, but yes, it is met. Because you're rolling it 10 times, and what you roll 1 time has nothing to do with the outcome on the next time, on the next trial. N is going to be 10, so we have a fixed number of trials, and P is our probability of success, which is 1 out of 6. And also P is sometimes referred to as S for success probability, and sometimes it's referred to as P. So you kind of need to know both of those. So yes, it is a binomial distribution. Okay, so shoot a basketball 20 times from various distances on the court. Let Y equal the number of shots made. So yes, we're looking for an outcome of a certain number of shots. We have a fixed number of trials. Here's the problem. Various distances. So this is going to be no, because the probability for success is not constant if you're moving all around the court. So it is not constant for each of the 20 trials. Okay, so observe the next 100 cards that go by and let C equal color. Well, this is not even a random variable because it's not numerical. So it has to be a random variable first, which means it has to be numerical. And this is abbreviating for because. It is not numerical. Okay, so I'm going to show you how to actually compute this. So let's continue on. In many games involving dice, rolling a 6 is desirable. The probability of rolling a 6 when rolling a fair die is 1 out of 6. If x equals the number of 6s in 4 rolls of a fair die, then x is binomial within a 4 and p of 1 6. So we kind of talked about that up above. And we want to know this particular outcome, 4 rolls. So what is the probability to have no dice that are going to land on 6? Okay, so we're looking for the probability that x equals 0, which is simply going to be the probability of all 4 failing to land on a 6. So in this case, this is just going to be 5 out of 6 to the 4th power. Now what I'm doing here, I'm just sort of setting up the formula for this because there is a formula we're going to want to use. So the probability for x to equal 1 is going to be x equaling 1. It could be the probability to have a success and then fail, 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 and then we would need the probability. This would be 1 out of 6, and then I'd have 3 failures, which would be 5 over 6 to the 3rd power. Then another way to get exactly 1 is to have a failure, a success, and then 2 failures. So then that would be a failure is 5 out of 6, and then I have my 1 out of 6 for the success, and then I have 2 failures, so I'd raise it to the power 2. Now, you notice that both of these cases I'm getting 1 probability for success and then 3 probabilities for failure, which makes perfect sense. So the question is, how many different variations of success are there? So how many variations? And guys, is this not just a combination? So I'm going to say how many combinations of exactly 1 6 exist? Is going to be 4, because it could be a failure, then a success, and a failure. So the way you would actually compute this binomial probability is going to be P of x equals 1 is actually 4 ways to get exactly 1 6, and then I'm going to multiply that by each of the probabilities that we would have for this, which would be what we sort of worked out before. So it's not just good enough to have 1 outcome of 1 success. I need to account for all 4 variations of 1 success, or 1 6. So I'm starting to kind of lay out the formula for you. Now, what about exactly 2 successes, or 3 successes, or 4 successes? Well, then you replace, instead of 4 variations or combinations, I need to figure out how many ways can you combine 2 successes. So what you have to do here, and guys, I'm really focusing on this piece right there first. So how many ways can I get exactly 2 successes out of 4? So it's going to be a combination 2 choose 4. This is going to be a combination 3 out of 4, and this will be a combination 4 out of 4. Now, of course, every single time the probabilities will change. So if you noticed up here, I had 1 as my exponent here because I was looking for 1 success. Here I had 3 because the other 3 would have to be failures. So these 2 will always add to the n value, or the number of trials. So let me kind of sum this up for you, summarize this up. How are we going to calculate these? Well, we're going to say P, X equals K, and this is just like X equals 2, for example. That's all I'm saying there. Is going to be C, and I'm going to choose K out of N, like I just showed you. And then I'm going to take my probability for success and raise it to the K power. So if I'm looking for 1 success, this would be a 1. If I'm looking for 2, this would be a 2, which makes sense with what we did up above. Then I need my probability for failure to all the other trials. So this is the formula. Okay, I will show you on the formula card, it's actually given as this notation. This is another way of saying choose K from N, and here order does not matter. Order does not matter. So it's this formula, okay? And you're actually going to use your calculator for this, but to get credit, you want to set up the formula, kind of proving you know how to use it, and to find the probabilities in the calculator. Now, I know some of you may be saying, well, why do we need to do that? Because if we can use the calculator, why can't we just use the calculator? Well, there's a lot of understanding that comes by using this formula that you miss by just plugging everything into the calculator. So setting it up is at the very least kind of ensuring that you're communicating that you understand this process at a deeper level. So that's really important to set that up. Okay, let's keep going. So we have a roulette example here. 18 of 38 spaces on the wheel are black. Suppose you observe the next 10 spins of a roulette wheel. So let's kind of specify what we have here. So we have N is 10. And if we're looking for success is landing on black, we need that probability. So it's either black or not in this case. And the probability for success is going to be 18 out of 38 because there are 18 black spaces. So what is the probability that exactly 4 of the spins will land on black? So you're going to write it out like this. Probability X is equal to 4 is going to be 10 choose 4. This is just going to be the combination. It's how many combinations of 4 are there if you're moving around the black spaces in the order that you get. Then I'm going to have the probability for success, and since I'm looking for 4 blacks, I'm going to raise this to 4, and then everything else, the probability of failure is 20 over 38, and then I'm going to raise that to the remaining trials, so 6. So that's how you would set it up. And then I'm going to actually show you how to do it in the calculator in tomorrow's notes. So you could do this mathematically. In fact, let me do that for you. Okay, so I'm going to first do my combination, and I'll show you how to do that. And then I need to raise the probability of success to 4 and the probability of failure to 6. And that's really all it boils down to. Okay, so I'm going to remember where your math is where you're going to go to for your combinations. But first I have to enter 10 because I'm choosing from 10. I go to math, I go over to probability, and remember it's NCR or option 3, and I'm choosing 4. Okay, I might go and get that value. So then it's just 210, and then now I'm going to raise 18 divided by 38, raise that to the 4th power, and then I need to do multiply by, I think that should work here, multiply by 20 over 38, and raise that to the remaining 6 trials, and that should give me the right answer, 0.2247. Now just quickly, just to show you, this is a very easy thing to do in the calculator as well. It's actually under our distributions. You probably have noticed it before, I'm not really sure if you have or not, but it's binomial PDF. And the number of trials is 10. The probability for success is going to be 18 divided by 38. And I'm looking for exactly 4 blacks here. And I get the same exact answer. So I just want to kind of show you, eventually we'll be doing it this way, but you need to understand it that way as well. Okay, so let's do the next one. What is the probability that at least 8 of the spins land on black? So I need to write this out as a probability that x is greater than or equal to 8. So that would be the probability that x equals 8, plus the probability that x equals 9, plus the probability that x equals 10. And these are pretty quick to set up. So this is going to be 10 choose 8. So the number of ways to arrange 8. And then I have 18, my probability for success, to the 8. And then my remaining 2 are going to be used there. So the probability of failure raised to the power of 2. Then I just do 10 choose 9, 18 over 38 to the 9th, 20 over 38 to the 1st. You probably have noticed these always add to the number of trials. And then I'm going to choose 10 out of 10. And then I'm going to have 18 out of 38 to the 10th. And then this remaining part is just the number 1, obviously, because I'm actually going to raise it to the power of 0. So this is just a number of 1. But that is how you would do it. You would set it up like that. And then briefly, let me show you how you'd want to do this in the calculator. So we have something called binomial CDF as well. And this is really tomorrow's lesson, but I just want to kind of show it to you. So I'm going to use binomial CDF, and I'm going to say my trials is 10. My probability for success is still 18 over 38. And now, if I'm interested in 8, 9, or 10, this is cumulative through a value that you put in. So I'm going to find cumulative through 7, and then I'm going to subtract it from 1. Okay, so I'll kind of show you that. So then all I'm going to do is just do 1 minus the probability through 7. Okay, and like I said, I'm going to go over this tomorrow. But this is how you would do it, and tomorrow's lesson will take you through that. But that should get you going for tonight's homework, and we'll pick up here tomorrow.